bit more about actual methodologies for data assimilation and try to explain, I hope it will become clear, why we need some of the information that came out of the background information I was giving yesterday. So we'll talk about two different approaches, which it's really the same approach, but one is called gradient, we just call it gradient descent. We don't have a better name yet. And the reason we're really keen on this method is it seems to work once we move towards imperfect models. So that's really our goal, is actually to find ways of generating an ensemble, a good ensemble of initial conditions in an imperfect model. You'll also see, as Chris pointed out yesterday, ISIS come up, an indistinguishable states importance sampler. This works extremely well when the model is chaotic and perfect. But of course, that's usually not the problem in operational centers. So mathematically, this has some very nice properties, which I won't really talk about at all. So I showed this graph yesterday too, and I got around 4 or 5 questions in the afternoon about it. So I thought I'd try to go back and do it again. So what we're plotting here is time is going up, right? And this is just the one value, the x value from the Lorentz equations. Remember, which have x, y, and z, or z. Is it z or z here? I can use 2 different variables. So one with a little bar and one without. Okay, so when I first start my data assimilation at time equals 0, I don't know the exact initial condition. So all I've done here is plot. Right, I've got a collection of 1,024 points, and I've just plotted a little probability distribution, just a little histogram here, to show you where those points are. Right, and then so from my point of view, the whole point of data assimilation is to get those points. Right, as many of them as I can afford to run. And then I put them in the model and I let go. And then the data assimilation people take a break and just watch what happens, right? And the PDF evolves in time. So this is going forward in time. And this PDF begins to spread out, and then it gets tight, and then it does all this interesting stuff. So what it's actually going to do depends on what you're forecasting. But the key is, in order to figure out how to get these, the key for data assimilation is trying to figure out how to get these initial conditions, right? And then if you have competing techniques, there's this other interesting question of how do you decide which is better? So I hope we'll be able to compare, at the end of the projects, a particle filter and gradient descent, right? And even if you've already decided what your method is, you probably have some things you have to decide as well, like how long should the window be if you're doing a variational assimilation. Right? They're just different parameters you'll have to decide, even if you've decided on theological reasons, right? Which data assimilation method you're going to use. So that question comes up again. And this is when it becomes important to look at those different kinds of probability comparisons we looked at yesterday. Otherwise, you're just sort of choosing at random. Okay, the other thing I didn't say is in this case, this particular PDF is accountable. So I was surprised to get a couple questions about accountable yesterday. What do I mean by accountable? Now, this is something we can only worry about when the model is effectively perfect. But, you know, we're trying to make a probability forecast, but we're doing it with only a finite number of initial conditions. So there's a chance, something like 2 over n, the number of points in our ensemble, that reality will fall outside the range of the ensemble. And because everything's nonlinear, it can fall very far outside. Okay. So this word accountable, which I don't think I'll say again, but the idea is that it actually lets you know how good the ensemble is, as good as it can be, given that it only has a finite number of members. Okay, so this is all very nice, right? But again, I'll ask you this question about 5 times, right? Once we move into the imperfect model, right? What is the point? What's the aim of data assimilation? So, as I said, my aim is actually to get an ensemble directly. An alternative is to just find a reference trajectory of some kind, right? So, like 4D bar starts out, it doesn't give me an ensemble. It gives me actually one trajectory. Then I have to make another pass to get that ensemble. The ensemble common filter actually sort of gives me ensemble, good to go, as does the particle filter. So that's sort of a nice property. what I'll talk about today, actually I'm not going to talk too much about ensemble formation. It'll mostly be about trying to find this reference trajectory. I also want to learn about the model error. So I think this is one really undersung positive aspect of data assimilation. Data assimilation can tell us a lot about what's wrong with the physics of the model, right? Not just the statistics. I mean, if we look carefully at data assimilation, the outputs of a data assimilation scheme, we really ought to be able to see what it is the model cannot do. So, you know, everybody can always increase the resolution and do some tuning here and there, but if we look at data assimilation more carefully, we can actually figure out what is it that the model can't do. What is it that if the model did this, say moist convection over the Pacific, the forecast would get better, right? Okay, so Emma last night decided to challenge the particle filter group, there isn't a particle filter group yet, to a head-to-head comparison with gradient descent. Does that sound okay? Okay, so this is what I'd like to do. We'll implement, Emma will implement gradient descent on, well, say we pick two systems, Lorentz 63 and one of your choice, or we'll just decide. And then we'll just see, right, which yields a better ensemble at the end, which yields better reference trajectories over 512 goes. All right? And just to make it more interesting, whoever wins, that team gets a copy of my book.
Does Emma need a copy?
What?
Does Emma need a copy?
Yeah. Yeah, she always, you know, she has about 6. I think Emma needs to read it, but. What?
512. What was the number 512 for?
So this is another interesting question, right? So how do we evaluate? I'm not going to have time to talk about it much, but now we have to. Eventually, because we have to compare these two systems. Anybody doing 40 bar is welcome to enter too. But we have to figure out how to compare these two data assimilation schemes. And so we need to do it over a large number of runs. So we want to look at a large number of completely independent segments of the trajectory. So pick 512 points, uniform on the invariant measure, and we'll test those. Does that make sense? Well, so that's another question. So how do you make the comparison fair, right? So so it could be the size of the ensemble. We get 512 and they get 3. It's not even a power of 2, right? So but there's another question. How do you compare two different data assimilation schemes? So, well, 40 bar only has time for one. So I mean, one thing to do is to try to put the constraint on total CPU time. So that's hard. There, the particle filter has a real advantage. We have an advantage against 40 bar, but this is an issue, right? This is a good question. In the graphs I showed yesterday, we gave the ensemble common filter infinite computational power, and so it had around 2 to the 14 ensemble members, and the ISIS method, the gradient descent method, only had 2 to the 8, and it still wins. So that's the kind of comparison I like. I don't think we can be that generous with the particle filter people. Okay, so I'm going to start talking again about the perfect model scenario. So again, as I said yesterday, in that case, the model and the system are identical. The mathematical form of the thing that generated the data is the same as the mathematical structure that's generating, that my model is using. And so there is a state called truth that's really out there, right? And I can try to find out what that is. And if I knew that value, I mean, you could say that is the goal of data assimilation. So when the model is perfect, it's a very well-defined problem. I only need one ensemble member. If I can put it on truth, I'm done. In chaotic systems, it turns out that truth isn't identifiable by noisy observations. And this is what indistinguishable states are, which I'm not going to talk about much, but let me just give you a feel. So in this perfect model scenario, right, that's truth. So what are all these pictures? Again, that's a point, and this is some high-dimensional space. And this point is at the end of a trajectory, which goes back to minus infinity. This is now. And what I assume I have, going back into the past, is just a series of observations. So the question is, what's the best I could do? Can I expect a data assimilation scheme, if the system is chaotic, can I actually expect it to tell me what this point is if I have even a semi-infinite amount of data, right, going back into the past? And the answer theoretically turns out to be no. Right? Because in a chaotic system, as you look going backwards, there are points which are very close to this point, which actually collapse down onto it. And once they get very close, they stay on top of it. There's no way taking more data back here will tell me which of these different states actually generated the data. Does that make sense? Right? So if I know the properties of my noise model, say it's IID Gaussian with some standard deviation, and I know the actual dynamical system, there is a set of states, even if this one is true, I can't distinguish with probability 1, right? This one won't be the maximum likelihood trajectory. It'll be one of these other guys. And as I go back in time, they all fall down on top of each other. So as the noise level goes down, these get closer together. As my sampling time goes down, these get closer together. But unless I have a perfect observation, there will always be an infinite number of trajectories that are indistinguishable from this particular trajectory. Okay. So again, in that case, the aim of data assimilation is well defined. What I want is this set of states weighted by the particular observations that I have. Okay. But in this case, even for a deterministic system with a perfect model and an infinite amount of data, I still have to make an ensemble forecast. The aim of data assimilation is still to give me an ensemble, right? Some kind of sampling from this distribution. So this is, if I say H of X, this is the set I mean. These are the indistinguishable sets of X. And if you like chaos, you can think about unstable manifolds and T going to infinity, but all that's going to go away when we get to the real world.
Why is it a subset of the unstable manifold?
So in fact, what I have, why isn't it the entire unstable manifold? So the unstable manifold of X will include points from even outside, from points which are very far away, which still fall down eventually onto X, right?
So you would have enough time to distinguish.
Right? And I need enough time, right? I need to go to minus infinity to define the unstable manifold. So this is a property.
This is a local versus global statement.
Well, so it's a property, the thing is it's a property not just of X, but it's also a property of the noise model, right? The noise model itself. So as the noise model gets, as long as the uncertainty in each observation gets smaller and smaller, then you restrict yourself closer and closer to t equals 0, the value of X. Okay? So, even if you don't, Chris does believe in these mathematical niceties, but even if you don't, right, you're still looking for the same sort of thing, right? You have to be looking for something like a set of states in the model that are consistent with all the observations that you have. And that's what this is trying to do, right? This is actually sampling the set of indistinguishable states of a point in here. Actually, it's probably one around here somewhere. It's not actually the truth, but it's going back and trying to find ensemble members, which as we go backwards, they get closer and closer to the center of the observations. Right, so most of the point, remember this is a very high dimensional space. This subset sits in a lower dimensional space. Most of the points in a ball at T0 end up going off and doing different things, including the points from the common filter. Okay. The thing to remember, right, is that once we leave the perfect model scenario, all these gray dots disappear. The thing I'm really happy with about ISIS, the reason now we talk more about gradient descent and a little less about ISIS, is it lies on this manifold. It lies very close to where all these gray dots are, the attractor of the system. Once the model becomes imperfect, that thing just disappears. We don't have that reference frame anymore. So, first for perfect models. What's happening? Well, we have these observations, the sort of red dots over there, right? What we want to find in the perfect model, we want to find some reference trajectory. So my reference trajectory isn't going to be the black line, but hopefully it's going to be one of these green ones that falls down close to the black line. But I only have to do that starting from just these observations. So how do I do that? Well, I have a sequence of observations. This is my S's from yesterday, right? And they said that each of those is in my n-dimensional space. I'm going to make a sequence space. I'm going to take a group of these, n of them, and make a point in a higher dimensional space. Okay? So this U corresponds to a series of vectors. These are the observations, these are the states corresponding to observations in my assimilation window. So any one of these, this is my cheap estimate of the current state of the system, or if I've observed the whole system, this is my observation of the current system. And now I have a whole set of n of these. Now I'm going to define a mismatch cost function, which is the cost function is defined on U, right? This entire set of vectors, and it's just the image of U at t minus U at t plus 1. Okay. So that's the graph we showed yesterday.
Sorry, F is the model.
F is the model. So the thing is sorry, you're right. This is a font problem. Right, no, so you're exactly right. But I don't want it to be S. So unfortunately, yeah, there are two different things. There are two different things on here. This U is actually the entire sequence. And this is the individual components of U. U with the subscript T are the individual components of U. Because I'm going to start with the observations, but I'm going to change what the value of U is as I move the algorithm forward.
Why you are taking two different times in the difference?
So I'm using, so yeah, so I'm using T and T plus 1. So let's say, so my big U, my heavy U with a pre-superscript, right, is equal to U, whatever it is, minus n all the way up to U0. So these are vectors. And at the very beginning, U0, I'm going to set these equal to the observations. So then at the very first step, this is just F on the first observation, right? The first observed state minus the second observed state. Right? So this is U sub 0. I map it forward. I actually miss U sub 1. Sorry, this is U sub minus T. I miss U sub minus T plus 1. But I think that's actually the picture that will appear if I push the button. So for some systems, like for the Lorentz system, for the examples we'll look at, we really observe the x, y, and z. But in fact, for other systems, we only observe, well, we have two problems. A, we don't observe all of the variables, and if we actually think it's a flow, there are an infinite number of them.
Suppose you measure a function of the state.
Sorry?
Suppose you measure a functional of the state.
Yeah, so it depends on what that functional is. So I can try to do, so really what I'll do is like assimilating the radiative field, right? So I will do that first. So we haven't looked at it really carefully, but what we do first is get just really a fairly sloppy analysis. And we would do that in the same way, trying to, however that's done. The key thing that's different about this method is it's trying to use information from the dynamics over a long window. And so far, having a not so great starting point hasn't hurt us, but it's certainly something we need to think about more. Okay? So what am I doing? What happened to the stick? So I take this initial, so this, your question, right? I'm taking this initial condition and moving it forward, and I'm looking at the difference between f on this value minus the actual next value. And the same thing again. And then at each point, there's a difference, a mismatch. This mismatch is just this term. The length of that is just this term. So my cost function is just the sum of the lengths of these misses. And instead of trying to move them, minimize them going forward and then minimize them going backwards, I'm going to minimize them all at the same time. So information will propagate in both directions. So I don't go forward and then backwards. I actually go into this space. This is trying to minimize all of these at the same time. So that if one of them happens to be too high, both the point before and the point after will suggest moving it back down. Right? And then that way we get much better noise reduction than, say, a filter that just runs through in the forward direction. And I think it's faster than going, the fancy ways of going backwards and forwards. We effectively propagate in both directions. So that's what we do. Okay? So this this next picture, everyone, I hope, will understand. Does Emma think everyone understands? You giving me odds? No. So what happens? I look at these, right? And then I just go down. This is just gradient descent in this higher dimensional space. And effectively, this was my S, but now this is U sub 1. This is the heavy U, right? So this U codes all of these points. And then I still have mismatches, and I go again and again. So as I go to infinity, or 42 in this case, I get something which is very, very close to a trajectory. Okay? But notice, I haven't put the observations in my cost function at all. Right? So I think for the same reason that particle filters have trouble in high dimensional spaces, we work better in high dimensional spaces. Right? We tend to fall onto the manifold. So, okay, let me say one more thing. Where is this 0? This cost function is only 0 when the image of u at times t is equal to u at t plus 1. In other words, when this is a trajectory. So when the model is perfect, I can actually integrate down very close to a trajectory, right? And I can actually look at a real trajectory. When the model isn't perfect, I probably don't want to go that far. Right?
That doesn't protect you against finding local minimum.
So there's only one minima. There's a manifold of minima, none of which are local in the sense that once you're on that manifold.
There could still be other local minima that you could get stuck in when you're creating the same.
But they're not. So Kevin can prove that there are no minima other than 0, and that 0 exists only on this manifold. There are no local minima.
If f is a nasty nonlinear function, that could be multiple minima.
Sorry?
If the model map function, f, capital F,
Right?
if it is a nasty nonlinear function,
Right.
there's a potential for multiple minima.
So in fact, so you can show, Kevin has proven that there just aren't. But that's right. A priori it's not obvious. What should be obvious to you is that this is only 0 when you have a trajectory. What isn't obvious but can be shown is that 0 is the only minimum for this.
But there are basically infinitely many minima, and the dimension of the manifold. So let me think this. There is infinitely many minima, and the space to which the minima belong is exactly dimension.
It's exactly.
M dimension.
So.
It's addition.
Yeah. So.
For every initial condition, there is a minimum.
Now I'm drawing a cross section of this space, right? So I'm starting out here, and now I'm in my m plus n dimensional space, and we're starting out here with an initial condition. And the gradient descent runs down.
Sorry, is this M cross N?
So m is the dimension of the model, n is the length of the window.
And multiply.
Oh,
I can't see.
you're right. You're right. On this manifold, the cost function is equal to 0. Every point on this manifold is a trajectory. So the only thing we're doing is finding a trajectory that is in some sense near the place we started. Right? It doesn't need to be particularly close. And originally, we had another term here which reflected the distance from the observations, right, with a multiplier on it, right? And it turns out that term just doesn't help in any of the problems we've looked at yet. But this is probably too much for a project, but we still don't understand really why it works so well. We have a couple ideas, but okay. So on this manifold, all trajectories of the system lie on this manifold. All trajectories of length n. We start somewhere, defined by the observations, and we just follow the gradient of the cost function to fall onto the manifold. So we actually got fancy ways of moving on this manifold if we ended up being far away from the observations at the end. But so far that just hasn't been a problem. Even using no gaps, right? Even with an operational weather model, that doesn't seem to be a problem. And this is, so what is this? Let me just go back. Now if you just look only at this particular point, right? What's happening here, in algorithmic time, we're moving this point around. Okay, actually we're moving this point around. And what you're seeing here is inside no gaps, and I think T42, we're looking at one point, right? One component of that vector fall onto the manifold. And so I think there are quite a few interesting sorts of things. You see this blob which was right here a minute ago? This was a data simulations attempt. There it is. This was a data simulations attempt to put a big storm. This is a vorticity map, right? Just to make sure. Here's India, right? Here's South America. Here's Florida. England somewhere in there. Right? Yes?
How this descent algorithm?
Sorry?
How this descent algorithm?
How did, I just got here.
You use gradient descent algorithm.
So this is the output of the gradient descent algorithm, and at iteration 0 is, I think, an optimal interpolation. Perhaps we tried to ask them if this storm was bogused in, okay? But then we just find the gradient of that cost function and just do normal gradient descent. We just find the gradient that minimizes those mismatches. And what you see here is the mismatch at the middle of the window. The window is, I think, 6 days long. And what I want to point out, see how the storm goes away, but then something else forms down here. Right? See how initially there's nothing happening in the middle of the US, and you end up getting this sort of long wave. You end up getting this larger structure forming. The same way you can see various centers of vorticity down here where we have very little observations. What's happening here, whether it's realistic or not, is another question. We hope to do a whole series of these, 512 of these. What's happening is the model is taking information from the future and the past and getting a state of the atmosphere that is as close to those values as this model can support. So it's balanced in the sense that not only is the normal balance conditions met, but it's balanced in the sense that it's very close to this trajectory manifold. It actually is taking information from the future and the past and trying to set up much larger scale things than you can ever get from a one-step filter. Right? It's actually looking for dynamical coherence over a 6-day window.
Can it be shown that the trajectory obtained as a result of this normalization would be the same as the one that would have been obtained had I used 40 watt?
So, no.
No. Why?
So, but it's the one that 40 bar would have liked to have obtained.
Okay, good. So what is the least square error property? So suppose you got the curve, and then the observations are going to be away from that. So there's going to be a least square, an amount of the sum of squared errors. How does that squared error compare with the one that would obtain by some minimization as a result of 40 watt?
So we haven't done 40 var on no gaps, but we looked at some of the ensemble statistics. But in general, the exact thing. This is actually, 4D bar has this component about the distance from the observations in it,
But you tacitly assume that.
right? And we don't.
So, but then if you apply your method to cases where you don't observe the real quantity but only a functional effect.
Right. Well, so again, so I avoid that problem by having shuffled it back into the optimal interpolation initial condition.
So somebody has
Right.
done some retrieval work before you started.
That's right, because almost always we just observe the state of the system, right?
Fair.
And I think that's a serious concern. But again, just using this cheap assimilation method, our main concern is, right? Our point is we have these bad observations of the state of the system. How do we actually find a model trajectory that's consistent with them? So the issue of getting those initial states of the system, those initial analyses, right? That's a problem in the weather context that doesn't hit us in the lab.
Listening to you, I now believe that you can get a nice trajectory. That's great. But I think there is a question of being able to compare the sum of squared errors.
So, in fact, I'm happy to do that.
Okay.
But I'm not overly worried. So the issue is how much do I believe that the sum of squared errors, when I've gone through this weird thing like assimilating radiances, is really telling me, how much do I really know about that sum of squared errors? What I'd rather have is a trajectory, what I'd like to have is a trajectory near truth. But I agree, we can compare with 4D bar trajectories. The difference we generally see is we can use a week. 4D bar is using 12 hours or a day. Right? So we can include a lot more information than 4D bar can. Once we did this, you could try to actually do 4D bar on this initial condition. When we have simple systems and short windows, it works very well. When we have a very long window, then 4D bar still goes astray, but the trajectory still goes astray. So the big difference is the difference in the cost function. We're actually looking for trajectories, and we're using the long window to get us on a good place in the manifold. We're not actually testing how close we are. We also don't make this assumption about the model noise. Okay? We don't know the properties of the noise. We don't need to make sure that the maximum likelihood trajectory under our model assumption. And we can use a really long assimilation window. So the problem with 4D bar is finding the global minima you want with a long assimilation window. And then if you use a short window, right, then you suffer because you don't have the information on the time scales on which the dynamics are interesting.
So every local minima that 4D bar will find,
Yeah?
assuming it has converged, will be a minimum of the cost function that you have.
Correct. They'll be over here. No, so 4D bar only sits on this manifold. 4D bar only lives where my cost function is 0. And that's its strength when you have a very good initial estimate, and that's its weakness when you have a long, when you don't have a good estimate.
Is the proof contained in your 2001 paper?
It's in, it's actually in the paper I'll reference in a minute, but it's Judd, Weisheimer, and Smith. And in fact, that minute is now, it's this paper. Okay. So what's this? Now we've moved to a T21 three-level geostrophic model, quasi-geostrophic model. Okay, so this is still perfect. And what I just want to illustrate, and again, this is a perfect project question, right? What I want to illustrate, and what we didn't really do right, is what we've done is we started with a window of 10 days, and we've made that window longer and longer and longer up to about 30 days. And because this is a perfect model scenario, I know where truth is. And I can see, as I make the window longer and longer, how much closer do I get to the true state of the system. So this is the distance from truth. And this starts out being the length of my assimilation window. And what you can see is, so this is 10 days. This is the noise level. 10 days, 11 days, 12 days. The longer the window, I keep getting closer and closer to truth, right? So this isn't 0, but this is significant. This is a factor of 3. Also, when I then just let go of the trajectory at this final state, right, then once I get out to about 20, I have much, much better forecasts than if I have the short windows. That make sense? So I'm actually able to use the information in this long window both to get closer to truth and to get closer to truth in a way which is not a bad dynamical direction. I actually get better forecasts from these initial conditions than I do from these. So it would be interesting to put 0 here and then do the assimilation going back further and further and further with Lorentz 63 or whatever model you want to code in MATLAB, and just get these statistics, right, over a variety of different initial conditions. Does that make sense? Good, good. And this is what it looks like, just to give you an idea of the size of the noise. This is a 3-level model. This is the actual, it doesn't come out. There's actually more happening in these 2 levels, but you can sort of see the motion. This is the level of observational noise. This is what we observe. Right. At the end, this is the shadow. This is the best trajectory, the reference trajectory that comes out. So you can see this actually looks really pretty good. What? So we're looking at this quasi-geostrophic model. We're looking at the same model.
What are the variables?
So this is the flow in 3 different levels. Right? So this is just a 3-level model. We're wrapping around the Earth. We're looking right. So you're just looking at the flow. You're looking at the field in a channel, if you want.
So the height field in each.
So this is X and Y, and there are 3 different levels.
Yeah, I got that. But what are the shadings? What's the variable?
So the variable is effectively velocity, right? So you're just seeing the flow. You're just seeing the flow in these 3 different levels. Sorry?
Magnitude of velocity.
Yeah. Okay. So so maybe this isn't the perfect example, but I think it's not so bad. What I want you guys to see, and even Chris, is first of all that this looks a lot more like this than this, right? Right. So you can actually see there's quite a bit of noise on this flow, and we're still getting it out. And also this question about RMS error. Well, I mean, we're not doing a perfect job. You can see that. So this is the implied noise. When we're done, we can also look at the difference between our estimates, our final state, and the initial noisy state. We see there's still actually dynamic information. There it is. There's still dynamic information in here. Right? Ideally, this would be white. So there's certainly still improvement to be made. Right, I'm going to come back to this again once we get to the imperfect model. Because I'm going to actually just skip forming an ensemble. But I want to introduce this for the projects as well. So this is one of the maps you saw a lot of pictures of. This is just to show you that the map it's sort of nasty, but it's not that nasty. It's just a 2-dimensional map that takes X and Y into X and Y one step further ahead. And the reason we like this map, and one of the things we'll have to think about as well, is we want to make a structurally imperfect model. It's easy to just change the parameters a little bit, but that's not really an imperfect model, right? That's just uncertainty in the parameters. You can still be Bayesian if you just turn the parameters a little bit. I want to break this by, say, taking something different for this sine function. And we'll show you how to do that in just a minute. Okay, so, and then what are these pictures? So you'll see these pictures coming out later in the exam. What do these mean? Well, this is the attractor on the background. This is just my climatological distribution. This would be my prior, right? These are just states that I'm trying to estimate at the crosshairs. Right? This ball gives you an estimate of the size of the observational noise, right? And what I'd really like to see, these sets are actually sets of indistinguishable states. So if the model was perfect, that's what I would look at. But we don't really want to stay any more time in the perfect model scenario. Okay, so this is the model we just saw. What I want to do is this is the system. Tildes are the system. I want to break this sine and cosine term. And I'm going to do that by just taking a 3-term expansion for the cosine. So I'm going to use the same equation, the same structural form, but instead of actually having the sine and the cosine of theta, I'm going to actually make a 3-term expansion for those. What that means is that my model is wrong now. I mean, my model is really wrong. I mean, it's really good. The one-step RMS forecast is really accurate. But if I try to iterate into the future, it goes off in the wrong direction, right? Very subtly in the wrong direction. And this is how it goes off. This is looking at the one-step ahead error, the imperfection error, where I am in space. So in this region, right? You could probably figure it out by looking at where sine and cosine are 0. In this region, the model error is very small. In this region, the little lines show you the difference between the true system and the model. The model error is large. And again, this is again where we have trouble with RMS. We generally are looking at, when we look at things like the noise function, we assume for the system, we're making averages over all states. If there's a hurricane here, right, the errors in that region can be huge. 2 days from now, the errors in that region can be very small. So in that case, there are no indistinguishable states, and all this stuff just sort of goes away. And again, if the model is chaotic, you can prove that there are no Kevin can prove that there are no indistinguishable states. As t goes to minus infinity, there are no trajectories at all that are consistent with the observations. So what are you trying to do, right? If you had, what would normally be you have an infinite amount of computer power, you have observations going back to t minus infinity, you've got your model, there is no answer. The traditional answer of trying to find, the state that generated the observations, it doesn't exist. So I'm going to skip this and go to the imperfect model scenario. Okay, this is what we just saw. So let's say we just want to keep a 4D bar-like approach and try to find the maximum likelihood trajectory. So these crosses represent, a very large numerical approximation of the correct maximum likelihood trajectory. So here's truth, here's the noise. If we just apply our method, we apply any method, assuming the model is perfect, with that noise, we end up getting these systematic, they're in different places in different places. We get these big crosses. Does that make sense? The maximum likelihood trajectory is the wrong answer if the model isn't perfect. So, and if we try to find, if we try to find ensembles, we end up getting ensembles that are very often far from truth. And here again, we sort of cheated. I mean, technically, this is a different space, right? Truth. The model is living in a different sort of space than we are. Okay. So, in the imperfect model scenario, the system state and the model state are living really in different state spaces. So, we really have to worry a lot now about moving between these two different systems. And this is just defining the things that we defined before. We don't have any trajectories that are consistent. We can start looking for pseudo-orbits, though. So now, before, what I wanted to do was take that mismatch and take it all the way to 0. Now I don't want to take it to 0 anymore, because my model isn't perfect. My model is very good, but I want to leave it non-zero in different places. So let's actually allow this omega, too many omegas here, let's allow this omega to be the mismatch that results after running my gradient descent for some period of time. So now I'm going to take this I'm going to run this for a while, but I'm going to leave a little bit, I'm going to allow a little bit of mismatch to actually account for the fact that I know my model is wrong when I start. This means that I'm going to confound observational uncertainty and model error, and I would give 10 to 1, you can't undo this, right? Given these two stochastic things, right, part of the uncertainty is going to be due to model error, part of it's going to be due to observational uncertainty, and we can't pull those apart. And then we stop looking for orbits so much, for trajectories, we start looking at pseudo-orbits. And this really isn't IID. There should be a reference to that, but, okay? So there's something else we have to do, which we have to agree on too, right? So now I need to make a model and a system, and I need those to be mathematically distinct. So you saw this before for the Akita system. This is the Lorentz 96 system. How many people have seen this before? 2, 3, 8. Okay, a couple. There are two different sets of variables. There's a slow set of variables on the outside and a fast set on the inside. If you really want to, I can play this as a movie sometime, but not now. And our system is going to be the Lorentz system, the whole system, both these two coupled cycles. And our model, which is imperfect, will just try to simulate this with an F. And of course, there's a whole list of different things you could put here rather than a constant. But again, that's another way we can compare two different systems. Same F or different. Right, so that's a great question, right? So these should everything here should have twiddles on it. What value of F should we use? That's a question. I mean, really, what value of F, how would you even define the value of F we should use? What properties should it have? Like, should it have the property that it gives you the best 5-day forecast? Because that'll be different than the value of F that gives you the best 1-day forecast or the best 10-day forecast. Right? Should it be the same on some sort of theological grounds that physically we know what F is? That's a good definition, but that will probably give you a worse forecast than any of the other two. Right? I don't have a good answer.
C is small.
Sorry?
C is small.
Yeah, we'll see. Yeah, so C basically allows us to how much we're coupling, right?
Well, it also covers the rates.
Yeah.
The Y's. The Y's are the slow variables.
So the Y's are the fast variables, the X's are the slow variables. So we're actually, these are supposed to be slow, large scale, right? And these are supposed to be fast, small scale. Okay, no, I'm pretty sure, well then B should be big. Right, so I really don't know why he set it up this way, because you see you very often but not always have this ratio. In fact, if you're really serious, there's another model in Lewin's 2004, which is harder to integrate, but it has some nicer properties to it. But we haven't worked with that one yet. Okay, so we do the same thing. We're back in our sequence space. Now we actually look at the implied noise. This is the observations minus the final state. And we also look at the imperfection error, which is just, this should be f of mu sub I minus mu sub I minus 1. This is just f minus f of mu sub I minus 1. This is the mismatch. So the insight of gradient descent is just to stop. Right? At some point, we leave these omegas, and we actually look at what this noise level is. And if we have a good idea of what this should be, we can actually use that, right? This tells us something about what's wrong with this, not just this, but all of these tells us something about what's wrong with our model. If we can go back and look and see if there's something, remember these are perturbations in the model state. If there's something that's missing in the model, these can give us a hint at what that something is. Now, you still have to go back and do the physics to figure out how to fix this. But these are the things, whatever these little vectors are, these are the things that are stopping our model from staying close to the observations. So it's a more principled way of trying to find out what model error is actually impacting you. And, of course, if we go all the way to a trajectory, we'd end up getting omega equals 0, right? But since we know the model is imperfect, we don't go that far. So another wonderful project question is how far should we go? So let's look at these graphs. So this is for the Akita map, which you should be able to do in MATLAB without trouble. This is for Lewin's 96, which I don't think we have yet in MATLAB. This is looking in gradient descent time. So this is an algorithmic time as we keep shrinking those mismatches. What happens to the implied noise? These solid lines correspond to the actual noise that was added, right? So in this case, we know what the noise was. And the noise initially, right, the initial noise goes up, and then it saturates. It actually gets too big. Okay? This is the imperfection error. How much do we miss by? The imperfection error comes down. This is what the true imperfection error should be, and then it gets too small. In other words, if we keep going out to these very large times, we're getting a trajectory, but now we have that problem that because we're not constrained by the observations, the nearest trajectory, because the model's wrong, the nearest trajectory is actually far away from the observations. And here is the distance from truth, because we know truth in this case. We actually get converged towards truth, and then eventually we start moving away from it in both systems. So what's happening in this case, right, is we're initially coming down toward a trajectory of the model, which is actually a much better trajectory, a much closer shadowing pseudo-orbit of the system. And then eventually we start wandering off towards the true model trajectory manifold, which is some ways away. The model just doesn't have a trajectory that's very close to the observations. So here again is an interesting question about how long should the window be and how long should you run this gradient descent. And we have rules of thumb, but we do not have a principled answer to either of those questions. But you can test it out.
So potentially the window is small, that will be problem for overfit.
When the window is small,
That could be potential problem for overfit.
that's right. So when the window, yeah, and that's exactly what, so when the window is small, then we tend to find we can get much closer to trajectories, but those trajectories don't and so that would be, you could show that, right? Someone could show that. Whoever you put in the group could show that. So, gradient descent minimization with intermediate runs produces more consistent pseudo-orbits. I mean, how do we do that when we don't know what truth is? Well, we usually have an idea what the implied noise is. That you can get by experiments, right? So we try to make sure that the noise doesn't get too big. Right? We try to get implied noises that are similar to the noise. We need to define, but we need to figure out a better way of defining in advance when to actually stop. And again, we can do this out of sample. So we do this with some tests to see when we get good forecasts. When we apply the same thing in toy models out of sample, and it actually works. And if you really wanted some other utility function, we'd be very open to trying to figure out if there's something better. I mean, what would be a better thing to look at, or how do you handle this question when you're assimilating something like radiances? And then let's go back. The last thing I want to show. It's just a couple of things on this imperfection error versus the model error. So this is a mismatch. This is an output, right? So with weakly constrained 4D var, you basically have to put in a model error covariance matrix. You have to say at the beginning the statistics of the model error. So we don't. The model error comes out. And we're happy it comes out because this is the way. This is the actual model error that you saw before as you move around the system. It's big in some places, it's small in some places, and it's not IID as you move around. This is the imperfection error we get with a very low noise level. So what you see, I hope, right down here where the model error is large, right, we're actually getting indications that the imperfection error is large. Well, the imperfection error is large. So it's saying that down here we have more misfit than we do up here. So we can actually look around the system, in this case, and see where the model error is large and where the model error is small. Right? This comes out of the analysis. So if you break a model, Lorentz 63 or IKEA or whatever you want, you can then do that same test, right? You can look at the regions where you know the model error is large. Does doing gradient descent actually identify those for you or not? Of course, we can't ever really know what that is, except in the toy cases. And then, as the observational noise gets higher, right? If the observational noise gets smaller, then we get a really good indication of the model error. This picture looks just like, as the observational noise gets larger, we sort of lose it. And again, I think once you have large observational error, this just gets convoluted with the model error, and I don't think there's any way to pull it back out. But if the observational error is small enough, you can. I'm going to skip weakly constrained 4D var, but this is the paper I was looking for earlier. It's a paper from 2001 written with people at ECMWF. So we actually looked at the model error over a period of time, and we can actually, and then we just took dot. So this is a vector in a 10 to the 6 dimensional space. We just took dot products on consecutive days, just to see how similar those vectors were. And it turns out that for 4 or 5 days, the model error has a reasonable persistence. Right? Those vectors are much more aligned than if you just take random model errors from around the year. Okay? So this sort of kills the idea of treating this by just a covariance matrix. And I almost want to stop there. I want to show you one more thing. So these are systems where we've actually deployed the gradient descent, and maybe we can do a new couple in the next couple of weeks. The one you're probably most interested in is this paper, which is the No Gaps paper. This paper has actually how to do it. So ideally, we need an adjoint, but we can actually try doing it without the adjoints as well. And the one with Weisheimer as the first author is one with the quasi-geostrophic model in it, which isn't up here. Okay. There are other issues, there are other ways of trying to do this to actually do parameter estimation as well. Okay. So, let's go back to this, because I just like it, right? So here again, what we'd like to do is to find a way of doing this even with a relatively, we'd really like to try to do a larger experiment than we could do with no gaps. And to do it over, a couple of the same season a couple of different times, and to do things like take the initial analysis, because the analysis should already exist, right? Take the initial analysis and compare it with the final analysis, and you see if things like this ridge, right? Just see whether or not we actually are seeing real things, or if we're just seeing things in model land, right? But the other issue here is we can actually look at the perturbations that are left, right? I showed you the little perturbations that were left in the case of the IKEA map. This is a mismatch in specific humidity for T47L 20 whatever, right? So for one of these two models. So this is from the geometry of model error. This is a picture of the perturbation that was needed to be made, an average of perturbations that needed to be made to specific humidity. Right? So the idea, I'm told, is that they know no gaps has some difficulty with its convection scheme in this region, right? But we didn't know that. The point is this comes out of the analysis. But one of the reasons that the no gaps model couldn't stay close to the data, one of the nudging, I guess this would be the direction you would want to nudge, right? This is sort of the control parameter that you need to push the model in order to enable it to stay closer to the data. So once you see this, you could then work on a scheme to improve the specific humidity. Like that's the idea. It's not just saying I have to improve everything. It's trying to find the particular perturbations that stop you from being able to follow the model trajectory. So in that sense, right, it tells you about model error, but it's not a stochastic fix. So this is the typhoon, right? This plane can't fly. Well, if it stayed the same, right? So this plane is aerodynamically unstable. Its wings have bunches of little panels and things, and it's constantly falling out of the sky. And then it's always moving it's moving its little wing pieces around with a feedback control system to keep it flying in a straight line, unless it needs to turn really, really fast, in which case it stops doing that, and that way it makes the plane very maneuverable. Okay? So if you took this plane and you took off, flew around the airport and landed, and you look at all those little perturbations that the wings made, it looks like a stochastic process. But if you tried to fly this plane with a stochastic process of driving the wings, right, it would fall out of the sky. So it's been suggested numerous times that these perturbations should just be introduced into the model, just make perturbations and make a stochastic process that perturbs the model around using those mismatch errors. That's not really the point. It's not that the process is stochastic, it's a control problem. In different places of the state space, depending on what the synoptic pattern of the atmosphere is, you need to make different control perturbations. Just like, depending on the state of the plane, you need to move the wings. So while they look stochastic, the information in them can't be simulated by a stochastic process. Which isn't to say stochastic processes are good things. It's just that you can't use our method to do that. And I think that's where I'd like to stop. Yeah, actually, I'd stop and take some questions then.
So there you're saying that the minimum is actually 0.
There I'm...
The objective value is 0. You can attain the objective to be 0.
That's right. So I need to say it in a way that I didn't say it before, or you still won't understand it, right? So I can always obtain a value 0 if I start by just if I just put f of u n minus, right, f2 so if I put a trajectory into this vector, then that's going to give me a cost function of 0.
Yeah, so what is preventing you from putting those values
Okay, so 4D var moves this value and this value only. We're actually minimizing, we're actually moving all the components at the same time.
Yeah, if all of them are free variables, then you said all of them are free variables, you're minimizing all the vectors, then you just set the next vectors to be the outputs of the function, f of un minus 1, and you get a minimum at 0.
But we do it via the gradient of that cost function, right? So we're just running, that cost function defines just a local field at this point in the space, and we're rolling down that field. So at the end, we end up with U42 minus n, and that's very close to f. Right? But by changing these values, we're approaching something which is a function. But we're approaching it in a distributed way. We're not trying to move the initial condition around and have that entire week-long trajectory wagging. We're actually trying to move the individual ones closer to being those images. We can, in fact, run the cross function to 0, but I don't think I answered your question. Maybe you can ask me afterwards.
And let me just want to make sure I have it straight. All the data does is the interpolation of the data to tell you where to start the ball.
That's right. So that we use the data twice. The first thing is where to start the initial condition. And then at the end, we use it actually to weight our ensemble members again. Right, so if we end up in a really bad place, right, we can tell that we're very far away from the observations. Sorry?
How to get the ensemble?
So originally we did a lot of work getting an ensemble by actually trying to estimate the indistinguishable states. What we do now, again, we're undecided. We basically we can just make perturbations of the midpoint, and this seems to be very effective at finding ensembles. We can also we looked a little bit at singular values. We looked a little bit at singular values with a forward operator, but they don't always point in interesting directions. Sorry.
To get an ensemble, so you start with some initial point which is close to the observations. When you come to a minimum, how do you get ensemble out of that?
Right. Sorry. So that's right. So we actually run until we get a value until we get a reasonably good pseudo orbit, and then we just perturb that pseudo orbit and then run the gradient descent again a little bit. So you can actually perturb at any state, but the earlier in the state you can perturb the observations, right? But the earlier you perturb, the higher the computational cost, right? What we tended to do is either just make perturbations to the pseudo orbits and iterate them forward, or make slight perturbations to the last pseudo orbit and run the gradient descent a few steps. But that again is an open, outside PMS, that's an open question. Inside the perfect model scenario, we look for the unstable manifold.